So let's start the last section of lecture 7. That's not the most enthusiastic lecture, optimistic, but those are partly realities about what's happening about our world. But now let's jump to a slightly different topic that kind of makes the link between glaciers, earthquakes, and volcanoes. And usually earthquakes and volcanoes mean bad things for glaciers. Here's just a small video about volcanic eruption that's below volcano in Iceland. In what is the name of that? Vatnajökull ice cap, where you have an ice cap in Iceland and some active volcanoes beneath it. And I think 15 years ago, something like that, one of the volcanoes erupted beneath the ice sheet. So what happens when you have a volcano that erupts at proximity of a lot of ice? It just melts everything super quickly. And what you have is a mega flood. Super interesting and fascinating event that washes out everything on its path, destroys bridges and everything. Luckily, it's Iceland, so nobody lives there and nobody got hurt. Yeah, makes a ton of damage. There's a bit of video. Okay, yeah. Anyway, you can look that up online with the link. So mega floods occur when a subglacial or periglacial volcano erupts and melts a lot of ice at once. I'm not gonna lie, it's not a very frequent event, but when it happens, it's super interesting. It has enormous destructive power, and for a few hours, that river that was created by that eruption and by the melting ice cap was several times bigger than the flow was several times bigger than the Amazon. So Iceland had the most powerful river in the world for a few hours. It didn't melt the entire ice cap, far from that, but it did melt a nice chunk of it. Another interaction between volcanoes and volcanoes and glaciers are beheaded glaciers. It sounds a bit dramatic, but that's what it is. We have a cool example of that in Alaska at Mount Katmai. So in 1915, Mount Katmai erupted, and there was a glacier in the caldera that was sitting there nicely. It was a Cirque glacier flowing out of there, becoming probably a valley glacier, pretty big chunk of ice, and the volcano erupts. It melts away, probably creates a mega flood somewhere. But after a few years, what happens? Well, the entire accumulation of the area of the glacier that was located in the caldera ended up going away. So that's why we call it beheaded glacier, because that's what happens when you have a volcano that just destroys the accumulation area of the glacier. So what happens to it? Well, basically it covered all the remaining ice that was mainly the ablation area in ash. It buried it in ash and debris and everything. And the interesting thing with debris on glaciers is that if it's a thin layer of debris, it enhances the melt. But after you pass the 30 centimeter layer thickness of debris, if you have debris that are thicker than 30 centimeters or so on your glacier, you will actually start insulate it very efficiently. So there are some glaciers that basically survive at super low altitudes and warm temperatures because they are buried beneath a bunch of debris. And in my bonus lecture that I talked about, that will probably come a bit later, that's a very interesting thing about the glacier I'm studying, the sit line in Southeast Alaska. Temporarily known as Malaspina Glacier. That glacier is covered by a forest in some places, and we are studying that right now and seeing that forest completely cuts the melt of the ice that's beneath. That's pretty interesting, super powerful insulator. And so basically when a volcano erupts and there was a glacier nearby, usually it has the power to insulate that glacier. And and what happens is that glacier, because it doesn't have an accumulation anymore, it's not fed by new ice. So what happens? It kind of becomes a rock glacier, some kind of weird thing that just creeps down and eventually at some point will melt out because there's no resupply in ice. But it might take a much longer time to melt out than if the volcano never erupted. Now, Earthquakes and glaciers. What happens when you combine the two? Well, tsunamis. The 1958 infamous Lituya Bay tsunami, that was the biggest wave ever recorded in modern history, with an estimated height of 524 meters. It's massive. So basically what happened is you have a glacier that's kind of behind that hill where the yellow arrow is. And that face of the mountain with the red arrow slid down during the earthquake, created an enormous landslide that went into the into that bay. And that made a wave that went over that hill and just went into the sea. So why is it related to glaciers? Well, that lake wouldn't exist, that bay wouldn't exist if it wasn't for a glacier. So that's how it's related. And there's a super cool story about that. When I was in Yakutat for my fieldwork, I met with Skip, a native guy who lived there his entire life, and in the 1958 he was pretty young, a teenager, and he was on the radio. So the earthquake happens, it's everybody, it's kind of everywhere because it hit Alaska pretty hard. But he was on the radio trying to listen what was going on after the earthquake, and he picked up transmission from the boats that were in Lituya Bay. And I remember, I don't know if some people died from that tsunami, but some people survived, and that's the incredible story. He picked up a transmission from a guy who was on a small boat that was exactly where the tsunami happened. So it wasn't like a wave, like you would portray a wave in Hawaii, but just 524 meters. No, it's more like a hill, a mountain of water that's moving down that bay. And the guy was saying on the radio, calling for help to come and rescue him, because he said, I'm stranded in the middle of there's too many trees around. And so people are communicating with him. It's like, okay, can you tell us what happened? It's like, yeah, so basically, well, I was there and there was a giant wave and he was transported on the crest of the wave, so up in the air by 500 meters and gently deposed into the ocean. And that's the crazy thing about it. That guy survived. And there are other stories like that. There's a few other boats to whom it happened. So that's real. And so basically, that giant tsunami destroyed everything that was on the ground, and like took with it entire chunks of forest. And so the guy is like, yeah, it took me away. I'm in the middle of the ocean. I can't move because I'm in the middle of the forest. And one of the guys on the radio is answering, well, how can you be in the middle of the forest if you're in the middle of the ocean? And the guy ends up saying, well, yeah, it took the forest, the wave took the forest with it, and right now it's completely covering the surface around me, and so my boat can't go anywhere. I'm blocked by dead wood in the middle of the ocean. Uh, so interesting story about, yeah, that gigantic tsunami that happened in Lituya Bay. And that's legit. I mean, there's a podcast about a little girl who was on one of the boats that got gently, I mean, I don't know if that was that gentle, but moved away by the tsunami. I can't imagine how scary that would be. Another example, a bit more tragic, is the 1964 Chinega tsunami that was caused not by a landslide over the water, but this time an underwater landslide. How is it related to glaciers? Well, that wouldn't have happened if that was not a fjord created by a tidewater glacier. And what happened is, below the ocean, especially around fjords where you have some kind of valley that's cut down and suddenly you have a drop to the seafloor, you have very unstable slopes at that transition between the fjord seafloor and the ocean seafloor. And what happens during earthquakes is you can have massive underwater landslide that just move a ton of water, and that creates tsunamis that then can propagate. So it's not necessarily the earthquake in itself that will move something, it's all that instability that when it collapses will create tsunamis. So yeah, interesting thing again. a bit more direct interaction between earthquakes and glaciers is Black Rapids Glacier in 2002 during the Denali Fault earthquake. So massive earthquake, very close. That Black Rapids Glacier is very close to the Denali Fault, so it really felt it. And what happened is you have an entire mountain that just collapsed onto the glacier. And you can still see that landslide today. It has just moved down, transported away by the glacier. So as you can see, it just crossed the valley that is a few kilometers large. And what happened is it completely changed how the ice is melting in the area, creating lakes up there that are sometimes draining through the moraines and everything. I mean, it's not even a moraine at that point. It's covering such a large chunk of the glacier. So this chunk of the glacier that's completely insulated by all that material is also melting way less than everything that's outcropping, all the ice around that's outcropping. So yeah, in that case, the glacier is kind of saved a bit by the earthquake, and we can see that there's another landslide up there that also occurred. Quiz prep: which two effects following the Katmai eruption impacted the Knife Creek Glacier? I will leave you a few seconds to answer that. The right answer here is answer B. The eruption destroyed the accumulation area and insulated the glacier by covering it in ashes, I could add, and debris. It's not answer A because no, the volcano did not uplifted the area. It's not either that, I mean, it might have created a mega flood at some point, but it did not freeze to increase the mass of the glacier downstream. It just does not happen. The eruption lowered the temperature of the area for years, lowering the EL of the glacier. Actually, that one wouldn't be that far-fetched, answer D, but that would be a bit, yeah, that would be a bit of a guessing game because go and try to prove that. So basically, answer B is the most straightforward answer. The eruption destroyed the accumulation area. It beheaded the glacier, and so kind of condemned it to disappear, or at least the lower part that survived to disappear at some point, but at least it insulated that part with some debris, therefore allowing it to survive for a bit longer. What is the primary source of a post-glacial tsunami in a fjord? Landslides of weakened snow slopes, massive calving at the terminus of the glacier, fast surge with a multi-decadal quiescent phase, or upper glacier lake flushing, creating a snowball effect in the fjord. The right answer here is answer A, landslide of a weakened slope. That was the case for those two tsunamis related to earthquakes and fjords. One was an overwater landslide, and the other one was an underwater landslide. So here's for the summary of this lecture. Smaller valley glaciers, tidewater glaciers, ice caps, and ice fields have dominated recent sea level rise. And if you take them individually, Greenland and Antarctica have been so far less of contributors than all the glaciers in the world, but that's about to change very soon. And of just the mountain glacier, of just the mountain glaciers component of sea level rise, Alaska is the region that contributes the most to sea level rise in that regard. But it is dwarfed by the amount of water that gets out of Greenland and Antarctica. And if you take all those components one by one, actually, and I'm just going to come back to that figure here. Yeah, thermal expansion accounts for a lot of sea level rise. That is not to be ignored. It is an important component in it. But again, if you take all that the ice is melting, it's still about 50% of the cake, or the cheese if you're French. Projected sea level rise will include increasing contribution from Greenland and Antarctica and depends on the carbon path of the coming decades. Again, we don't know for sure what the future holds for us, but that is something we know is going to happen. Greenland and Antarctica will have increasing contribution. They will melt more because as we study those systems, we discover instabilities more than we discover stabilities. So basically, our projections are ever optimistic and we adjust them as we discover things. There's one thing that I want you to take away from that whole course is that the material I'm teaching you, a lot of it will probably be obsolete in a decade, in the sense that the principles, how glaciers melt and stuff like that, that's going to stay true. But those projections, those numbers might not be true in a few decades, because science is forever evolving. Sometimes we discover new processes. Sometimes we invalidate processes that we thought were real and good. But that's the process of learning. That's how it works. So always be very critical with the information that's given to you. Always ask for the sources, and I think these lectures could do a better job at providing some sources. But if you want more sources, please reach out to me and I'll be more than happy to give you the links to all that. The IPCC reports are a great way because to go through all that material. Yes, it's thousands of pages, and even I don't read everything, but it's a gold mine for information. So yeah, that's the projection for the future. And average global sea level rise can be a misleading term, because sea level rise does not vary everywhere, is not the same everywhere in the world. Sea level rises varies regionally depending on the rate of uplift, for example, but also where you are in terms of, if you're on the equator and the temperatures are higher, you might have more thermal expansion and stuff like that. Subsidence of coastal areas is also an issue. So average global sea level rise is really a blanket term, but when you take a bit more precise look at it, you will see variations pretty significant. Let's go for one final quiz prep. So assume climate warms significantly. How will the following variables change? So climate becomes warmer, the ablation will, I'll let you put on pause right now if you want to answer everything by yourself, but I'm just going to go through the answers. So warming climate, ablation will increase because you have more energy to melt your glacier. The mass of the glacier will decrease because you melt it away. The mass balance will be more negative because you will melt more material than you will accumulate. Therefore, the ELA will go higher because the ablation area is increasing on the glacier. And so the ELA goes to a higher altitude and the accumulation area reduces in time. So accumulation area becomes smaller and the glacier tongue will retreat. That might be up for discussion, all of those points for a tidewater glacier. And actually, that's a good takeaway point as well from this course. Those might not be necessarily true if you look on a case by case for a very specific glacier, all of that. That's why it's super important to be critical. But if you look for overall trends, that's what would happen. And that's the goal of this course. I'm not aiming to make you glaciologist, but merely to give you an introduction to all that. And as an introduction, this is good enough. Assume climate hypothetically cools down. What happens to all these variables? If the climate cools, the ablation will decrease because you have less energy to melt away your material. The mass of the glacier will increase because you will melt less ice. The mass balance, therefore, will become more positive because you accumulate more, or at least you ablate you ablate less ice. The ELA will go lower because the accumulation area will become bigger, so that equilibrium line altitude will go down as the ablation area recedes. And the glacier tongue will advance after some time because you create more material, it has to go somewhere, and the glacier becomes a bit more heavy in a sense, so it's flowing down, it's advancing because you create material. Okay, that was it for the last lecture. I'll try to make that bonus lecture happen. You won't have any question on that bonus lecture. The question quizzes are already online. Sorry, they're already done, but please let me know if you need more help to understand a specific concept. I'm available. I have those office hours on Tuesdays and Thursdays at from 2 p.m. to 2:30 p.m. and I'd be happy to stay longer if you want me to. But yeah, I hope you had a good overview of the world of the cryosphere during those 7 lectures. I hope I was engaging enough and the material was up to your expectations. That the labs, for those who them, were learning you many things and new skills. As always, it's really funny great to teach that course, because it is much more comprehensive than what actually you would expect from just an introduction. We go pretty much in detail, so you can be proud of yourself if you made it that far. And even if it was really hard, that you learned a lot of things. And so really, like I said in that introduction video that I put online, I just hope that your main takeaway from that course is that next time you're somewhere outside, you're walking in a place where there were a glacier or there are glaciers, you'll be able to remember some of that and be like, I know how it works. I know some of that. I can transmit that knowledge to other people, because by 2050, there will be way less glaciers on this planet. And so it's always super cool to transmit some knowledge about things that are a bit threatened in a way. That's kind of a bittersweet feeling, but you see what I mean. Yeah, I just hope you learned things, that you were happy with that, and that I did at least hopefully a good job in transmitting the knowledge and the passion of that. So have a great evening, day, end of the week, whatever time it is. And yeah, if you see me on campus or around, don't hesitate to stop me and have a discussion. I'll be more than happy to talk to you all. It was a blast, like always. And well, see you next time. Bye.